Here are the answers for section 6-2 functions, starting with the oral exercises. We have a graph, and the question is the relation a function? We're going to answer that yes or no. If we say no, it's not a function, we have to explain why. And if we say yes, that it is a function, we need to give the domain and range. So number one, there are a bunch of ordered pairs. A function is a relationship between x and y coordinates so that every x coordinate is assigned only one y. Every x value can have only one y value associated with it. So to decide if this is a function, we need to look at the dots and see, do we ever have a situation where an x coordinate has more than one y value with it? And we do have that. If you look down this column right here at this dot and at this dot, notice they line up vertically. They both have the same x coordinate but different y values. This dot right here is 1, 0, and this dot right here is 1, -2. So the value 1 in the domain is not assigned only one value of y. There are two different y values that go with x equals 1. This is not a function. To explain why, we're going to give that as our reason. Because there are two y values assigned to one x value. Because this is not a function, we're not going to give the domain and range. Now number 3, we have this segment graph. To be a function, every x coordinate can be paired with only one y coordinate. That seems to be the case. As I look along the entire segment, I don't see anywhere where there's something lined up vertically with the segment. So this is yes. And our reason is that each x value does have only one y value. Because we answered yes, we're going to give the domain and we're going to give the range. What are the x values in the function? This is the origin, this is -1, and this is -2. Going to the right, it stretches over to +2. So the domain appears to be anything in between -2 and +2. What about the y values in the picture? This is the origin, so this mark down here is -2, and this mark up here is +2. The y values seem to go from a height of -2 up to +2. Number 5, here we have our picture again. We want to know if this is a function. Is every x coordinate paired with only one y value? Do we ever have a place in the graph where something lines up vertically with another dot in the relationship? I don't find anywhere where that's true. So yes, this is a function. Each x value is paired to only one y value. Let's give the domain and the range of this relationship. The x-axis seems to go from right here at -3 all the way across to here at +3. That's the domain. The y-coordinates seem to go from this height of -1 up to this height of 0. Number 7, is this a function? Is every x value paired with only one y value? No, it's not. For example, looking at this dot and this dot, these have the same x coordinate, but they have different y coordinates. Right here's the origin. So this dot is at 1, -1, whereas this dot is at 1, 3. So what y value is paired with x equals 1? There's two different y values assigned to x equals 1. That's not a function when you have that. No, because there are two y values assigned to each x value. Visually, when something looks like it overlaps something else in the graph vertically, that is when we say not a function. Number 11, do we have any vertical overlap? We do, in multiple places. So this is not a function because there are two y values assigned to each x value. There is vertical overlap. For example, this dot and this dot. They both have an x-coordinate of 1, but the y value is -1 here, and the y value is +1 here. Two different y values for that x value. That's not a function when you have that. Number 13, we don't have a graph, but we do have a list of ordered pairs. We could graph them if we needed to, but let's try to focus on the definition of a function. To be a function, every x value can have only one y value. Let's look to see if we have that. Here, x is 1, and it is assigned the y value -2. Is there anywhere else in the list where x is 1, but it's assigned a different y value? Well, no, we don't have any more ordered pairs where x is 1. In the second ordered pair, x is 2, and it's assigned the y value of 3. Are there any other ordered pairs that have an x of 2, but a different y value? No, I can't find any. Finally, when x is 3, y is 4. When x is 3, it looks like only the number 4 is assigned to it. So this is a function because each x value is assigned only one y value. Because it's a function, we're going to find the domain and range. The domain is a list of all the x coordinates. There's a 1 and a 2 and a 3. The range is a list of all the y coordinates. There's a -2 and a 3 and a 4. Number 17, when x is 2, y is 1. But later on, when x is 2, y is 2. There are two different y values assigned to the x value of 2. That's not a function when that happens. Number 25 has different directions. We're given a function called function f, and we're given an equation for the function, or a function rule. F of x equals 3x minus 1. Find the following numbers. F of 0. To evaluate a function means to replace the variable with the number that you're asked to evaluate at. So when x is 0, what does function f turn out to equal? 3 times 0 minus 1 is -1. For the same function, what do you get when you substitute -1 in place of x? -3 minus 1 is -4. Now the writtens. We're given a function called p, and we're given the function rule, or the equation for p, and we're asked to evaluate at these different values. So substitute in 0 to see what the value of function p is. When x is 0, p is 1. Now let's evaluate using a 2. Two squared is 4. 2 times 2 is 4. And then when you add 1, you get 1. So when x is 2, p equals 1. Now let's substitute an a where the x is. So a squared minus 2 times a plus 1. This doesn't simplify anymore because there aren't any like terms. Number 9, we have a rule for f and another rule for function g. We're asked to find g of 0. So make sure you're using the correct rule. We want to use this rule over here, not the one for f. So substitute 0 where x is and figure out the result. When x is 0, g equals -3. Number 11, we want to go 3 times f of 0. So this one uses the rule for f. So use this one here, not the one for g. We have 3 times, and then to find f of 0, we're filling in a 0 where the x is. This is 3 times 3, which is 9. For number 13, we want to find f of 1 and then subtract g of 1. So let's first put a 1 in for function f. That becomes 1 plus 3. Then we're going to minus g of 1. So let's put a 1 in for function g. 1 plus 3 is 4. 1 minus 3 is negative 2. And 4 minus negative 2 makes 6. In number 17, we're asked to graph something. The function rule is f of x equals 5. F of x is always the constant 5, no matter what x is. We're asked to graph it twice. First, if we use only integers for x. When x is the integer negative 5, function f equals 5. So negative 5 comma 5 is a dot up here. When x is the integer negative 4, function f has a value of 5. So that's a dot up there. When x is negative 3, function f is 5. So another dot up there. Do you see the pattern of the dots? So just put a horizontal row of dots across the grid. This continues forever to the right, and it continues forever to the left. Now question B. Let's do the same thing, but this time use real numbers. So this time x can be all the integers, but can also be decimals and fractions. For example, when x is negative 5, function f has a value of 5. When x is negative 4.5, function f has a value of 5. When x is in between negative 4.5 and negative 5, there's still a dot at 5. Do you see what's happening here? No matter what x is, no matter how close together x is, we always will get a dot at a height of 5. The fast way to draw that is with a line. In an earlier chapter, we learned that that's called a linear function. Number 21, we have a table of values, and we're told that it makes the function called t. Find the domain of the function. The domain is the list of all the x values. So that's a 1, a 2, a 3, and a 4. Now we're asked to write a formula for t of x. We want to write down t of x equals, and then figure out an accurate formula. To do that, we have to look at the values in the table. Let's first check to see if this is a linear function. Is there a constant rate of change? When this increases by 1 unit, this increases by 6 units. When this increases by 1 unit, this increases by 6. When this increases by 1 unit, this one increases by 6. Our rate of change is an increase of 6 every time x changed by 1. That's 6. And this is called slope. We use the letter m for slope. We know that the slope is 6. We also have 4 points to choose from. If we choose the first ordered pair, that's 1, 7. We have a slope and we have a point. Let's use point-slope form. We're used to point-slope form using y and x. We don't have a y this time, we have a t. But let's start by using y, and then right at the end, finally change it to be t of x. So point-slope form, using the letter y, is y minus y1 equals m times x minus x1. Let's make substitutions. For y1, fill in 7. For m, fill in 6. For x1, fill in 1. Now let's solve this for y. We have y minus 7 equals 6x minus 6. Now add 7 to both sides. Y equals 6x plus 1. That's how we wrote the equation in an earlier chapter. The only thing different in this chapter is we're not using the letter y to name our function. We're calling it t. So t of x equals 6x plus 1. Here's our function formula. But we got that answer by using what we learned in the early chapter about linear functions. Number 25, we have a rule for function r. We have a different rule for function t. Let's find t t of r of 0. What this means to do is to first figure out r of 0 and get the number for that, and then substitute that number into function t. So this is a two-step process. Step 1, let's find r of 0. Take the rule for r and substitute in 0 for x. That makes -1. Now that we know what r of 0 is, we can substitute -1 into function t. And this makes 0. So t of r of 0 makes 0. Number 27, same idea. We're going to do this first to find out what this number is, and then substitute it into the r. So step 1, let's find t of 2. Take the rule for t and put a 2 where the x is. This makes 9. So now we know that this part inside here just turned out to be 9. So we want to find r of 9. That's our step 2. R of 9. 3 times 9 minus 1. And that makes 26. Finally, number 31, we have a rule for function p and a different rule for function q. If x is 5, let's find p of q of x. You have to do this one first. So step 1, let's find q of 5. Put a 5 where the x is, and evaluate this answer. 2.5 subtract 3 is -0.5. Now let's do step 2. Take the -0.5 and plug it in to function p. So we're finding p of -0.5, and we do that by using the rule for p and filling in -0.5 where the x is. 2 times -0.5 is -1. -1 plus 6 makes 5. Question B, let's just flip this around. Let's first find p of 5. So take the rule for p and fill in 5. That makes 16. Then in step 2, substitute 16 into the q. So we have 16 over 2, take away 3. This makes 8 minus 3, which is 5. Notice that we got the same result no matter which order we had our function composition. In the future, we're going to learn a vocabulary word for that. Whenever two functions give you the same result, when you switch the order of their composition, they are called inverse functions. That's going to come up later this year.